Yes, thank you very much, Indranil, for this such a very warm, very nice introduction. It's a great pleasure for me to give a talk online in Hyderabad. Unfortunately, I've never been to Hyderabad, but I know what I know about this city, that in 2010 you held the International Congress of Mathematicians. So Hyderabad is now is a known city on the mathematical map of the world. So it's a great pleasure to give a talk. Yes, I mainly in this talk I represent German university, the Heinrich Heine University Düsseldorf. Simultaneously, yes, that's true. I work also in Russia, at least yes, affiliated. Currently I'm speaking from Russia. That's why I had some connection problems. Yes, the talk is multiplexed quantum repeater rates in the stationary regime. This talk, I'm not sure, maybe the title of the talk on slides is slightly different from the title I announced, but it's actually the same. I'll explain the difference later. What is this talk about? In this talk we will analyze discrete time Markov chain. We will analyze performance of the chain of quantum repeaters, and equivalently a slightly different scenario of multipartite GHZ, Greenberger-Horn-Zeilinger switch. So these are different objects, two different objects, chain of bipartite quantum repeaters and multipartite GHZ switch. But we will see that these two models, at least in idealized setting, are mathematically equivalent, and we will analyze their performance in the stationary regime using the tools of discrete time Markov chains. And the main result I would like to present is a new approximation of this Markov chain based not on particular values of parameters, not on perturbation theory, but on universal properties of probability distributions, such as the law of large numbers and the central limit theorem. And this approximation is good and have excellent agreement with the simulations for the whole range of parameter values. The talk is based on this common work with Julia Kunzelman, Nikolai Widerka, Hermann Kampemann, and Dagmar Bruce from the Heinrich Heine University Düsseldorf, published yet only in archive, but hopefully soon also in a journal. The plan is as follows. So first, I recall what is entanglement swapping and quantum repeater. Then we will describe quantum repeater as a Markov chain. Then we will consider further developments like memory multiplexing and GHZ switch. And then we consider two different approximations. First, approximation of rare events, when actually a perturbation, a kind of perturbation theory. And our main result, number 5, the simplified Markov chain based on approximation based on universal properties of the probability distributions. And results, stationary entanglement generation rate. So what is the problem? Quantum communication is a practical field, so maybe most news about quantum technologies come now from quantum computations, but quantum communication is closer, maybe closer to practical applications, more first of all quantum key distribution, but other applications are also under development, like entanglement assisted communication, direct quantum communication, and so on, quantum digital signatures. And we hope that in future we will build large quantum networks, and sometimes people say even about quantum internet. It's useful for communication and also for quantum metrology to increase measurements and time synchronization, which can lead to further to breakthrough in physical experiments in quantum gravity and so on. So we need like quantum sensors communicated quantumly with each other globally on the Earth globe. And but then we need to solve the problem of long distance quantum communication. So present day quantum key distribution or entanglement distribution allows us to communicate via relatively small distances, like hundreds of kilometers. But we want to have long distance quantum communication. And in classical communication, this problem of long distance communication, overcoming the absorption of the signal, decay of the signal, is solved by the concept of a quantum repeater depicted here. Classical repeater, or concept of a repeater. What does repeater do? Repeater receives a classical signal and retranslates it or amplifies to extend the communication distance, and we can enjoy the global communications. And in the quantum field, this problem is even stronger because quantum signal is much weaker. For example, the single photons or quantum coherent state, but with low intensities because it must be quantum. So if the problem exists for intensive classical communication signals, then of course it's this problem is much stronger and much more difficult for quantum communication, which uses very weak signals with single photons or few photons. Unfortunately, the famous no cloning theorem forbids such kind of solution in quantum communication, at least direct generalization of this classical solution for quantum communication, because unknown quantum state cannot be cloned. What a classical repeater does is actually clone the state, so receive a signal and then amplifies it. In the quantum case, it's impossible. Quantum no cloning theorem forbids the cloning or amplification of an unknown quantum signal without introducing noise. So the idea of classical repeater cannot be applied directly, but fortunately, people suggested a different solution. We will consider a bit later. Now, what is the goal we will consider in quantum communication? The first goal we can consider is to create an entangled state between two terminals, Alice A and B, or Alice and Bob. They want to create one of four Bell states, which are depicted here. Some slides here I used in the talk for mathematicians not familiar with quantum information. So here I give some comments that yes, these states live in the space of tensor product C2 times C2, and they are called entangled. This means that these vectors cannot be represented as tensor products of separate vectors in one copy of C2 and the other copy of C2. So these are entangled states, and such entangled states can be used in quantum cryptography, in entanglement assisted communication, in quantum metrology, and so on. And imagine that the source of Bell states is somewhere in the middle between Alice and Bob.
Hi, can I have a question?
Yes. Sure.
So this success probability, that is P is equal to 10 to the power minus alpha by L. Here alpha is the, I think, the attenuation loss, right? And
Yes.
L is the length of the fiber. But I think that there should be another factor, which is minus alpha L by speed of the light in the fiber. Um because that success probability is 10 to the power minus alpha L by this C, which is the speed of the light in the fiber. Then that gives the time. Uh,
Uh, I think speed of the light is not directly relevant here. So of course it's relevant if we consider propagation of signal. But
because
this
this
is
is heralded
not
photon
about the
radiation,
rate.
right?
This is not about the rate in a sec yet. This is about of whether you receive the photon or not. So
Okay.
imagine that the problem is that if L is the distance, then yes, then and Alice and Bob use optical fiber for signal transmission. Then a photon is absorbed according to this law. So it's the probability of success of successful transmission of a photon decays exponentially with the distance.
I was thinking of this is fine means, but I was thinking that is what I have seen, that it was minus alpha L by D. That's why I was by C. So I was thinking that if I am missing a point over here or not.
No, alpha is not related to speed of light. So speed. So of course it takes time for a photon to get to Alice or Bob from some central station. Of course it takes time, but here alpha is absorption coefficient is typically 0.2 decibel per kilometer for optical fiber. So it's not related to the speed of light because it's not about the time propagation. It's okay, you wait enough time, so it takes time. I don't know how
Okay, fine.
it takes time, but you wait this time for this photon to reach you. For example, if you are Bob and you wait for the photon for the central station, you know how much time does it take to arrive. You wait for this time, and that's what is the probability that you will get the photon, or the photon is lost somewhere. So so of course it takes time, but here it's not about time. Time is is known, but here it's about absorption of the photon in the optical fiber, and it's
In this case, when you are saying P square, you are referring to two detectors, right? And the second case, both the photons. So
yes.
P square, two detectors on either side. That's why.
Yes, for success, both photons must
Ah,
reach the corresponding user, and so total success probability is P squared. And alpha, as I said, is 0.2 decibel per kilometer. This means that this probability decays in 10 times every 50 kilometers. So so if you send a photon over the distance of 50 kilometers, then your probability is 1 over 10. In 100 kilometers, 1 over 100. 150 kilometers, 1 over 1000, or that is only each thousandth photon successfully reach, for example, Bob, and approximately 1,000th reach Alice. So in total, you have one photon per million successfully. Sorry. one round per million is successful when both photons reach the corresponding stations, and of course it takes time, but we don't consider it here. Okay.
Okay. Please carry on. You
Yes,
can
thank
ask
you.
later.
Then how to improve this situation, and people suggested so-called entanglement swapping. So let's consider
Excuse me.
Yes.
Yeah, so like how is that formula derived, like the probability in the previous slide that it decays exponentially with the length? Like how is the or the intuition, like how do you like calculate, like okay, there is loss, so I mean that way I know that okay, with length the probability of detecting will decay, but this exponential relation, can you give some intuition or something?
Mathematically, if you imagine that on each, I don't know, small divide the whole distance in very small segments, and probability of being lost in each segments are independent of each other. So or events being lost in each segment are independent from each other. Then mathematically this will lead to exponential decay, like a Poisson process.
Oh, right. So it's like at some distance, the probability of detecting is something. Then the next point, it's again the same probability distribution. So at the
Yes.
end, it's like p to the some okay, I got it.
Yes. Yes, thank you for the question. So yes, in principle, of course, I agree about the previous question. L is somehow related to the speed of light is not here, but we can think, of course, like in time, like photon goes through the fiber, and in each segment it can be absorbed. Probably, moreover, probably, of course, the speed of light. So I said that alpha is 0.2 decibel per kilometer. How one physically can derive this constant? I don't know, but probably here how to derive concrete alpha. If we have an optical fiber, then we solve Maxwell equations in the fiber, and somehow we can derive alpha here. So maybe speed of light is implicitly lives in alpha. Why alpha is 0.2 decibel per kilometer, not 0.1, for example, decibel per kilometer. Probably speed of light participates in the derivation of alpha.
Yeah. I was thinking because most of the papers that I have gone through, I have seen that this L by C is there. So that's why I was wondering that whether it is there in the alpha itself. You can always change alpha accordingly.
Yes, so for me, alpha is just a constant. I take it for granted that alpha is 0. Typical value of alpha for optical fiber is 0.2 decibel per kilometer. But of course, somehow it is derived using Maxwell equations for optical fiber, and of course, speed of light is there in this derivation. Okay, so now entanglement swapping. We have an intermediate station. And now we have not one source of entangled states, but two sources. So one source between A and this station, and another source is between B and this station. So the state, the total state, is phi plus, tensor phi plus, and or it can be decomposed into such a superposition, or if we rearrange the ordering, not A C1 and C2B, but AB and C1 C2, then this state can be rewritten like this. And then we see that if the station C performs C from center performs the Bell state measurement. So measurement in the basis phi plus, phi minus, psi plus, psi minus. Then the state of A and B also collapses into the corresponding Bell state. So this central station performs the measurement or entangling measurement between C1 and C2 and get, for example, phi plus as an outcome. It communicates outcome to Alice and Bob, and then they know that their state is also phi plus. If C, the central station, gets, for example, not phi plus but psi minus, also it communicates this result, actually 2 bits, one of 4 outcomes, 2 bits. Then Alice and Bob know that their state, their new state is also psi minus. So the state of A and B also collapses into a Bell state, though photons of A and B did not interact directly. And one can show this decomposition, which is crucial here, either directly, if we apply simple algebra, if we substitute these formulas and consider tensor products, or using stabilizers. It's known that the state phi plus is actually all Bell states are eigenvectors of 2 operators. For example, consider these Bell states xa xc1 and za zc1. So xx and zz are so-called stabilizers for phi plus. So and all Bell states are so for all these 2 operators, xx and zz. And so xa xc1 leaves invariant phi plus, and xc2 xb leaves invariant phi plus c2b. Then their product leaves invariant this tensor product. And if we rearrange now the factors, we can write xa xb times xc1 xc2, and also the same for z. And measuring c in the Bell basis means that we measure here simultaneously xc1 xc2 and z c1 zc2. These are commuting operators. X and z do not commute, but xx and zz commute, and we can measure them simultaneously. And if we fix these 2 observables, they can be either +1 or -1, and we fix the result, the state, that our total state collapses into a state with a definite value of xc1 xc2 and definite value of zc1 and z times zc2. Then also, since the left-hand sides are fixed and these blue factors are fixed, then the red factors are also fixed, xa xb and za zb, and depending on their values, psi +1 +1 +1 -1 -1 +1 -1 -1, we get the corresponding Bell state, phi plus, phi minus, psi plus, psi minus. So this decomposition one can show either directly, directly, or more from the structural point of view, from the point of view of stabilizers. This is, of course, not our results. It's I simply remind some known things, but which maybe will be useful later. And so, after the Bell state measurement of C1, C2, the state of A and B also collapses into a Bell state. Then the strategy of quantum repeater strategy: establish 2 entanglement links separately. So establish an entanglement link between A, C1 and between B and C2 separately. There is no advantage yet, because still, in order to still in total, the whole distance between A and B must be overcome. So neither. So we in total we have 4 photons, and no one can be absorbed. If at least one of these 4 photons is absorbed somewhere, then everything is lost. Without so in order to get advantage, we need a quantum memory. So if only one link is successful, for example, AC1 is this link is established successfully, and one of 2 photons between C2 and B is absorbed somewhere, and so the establishing the entanglement link between C2 and B is not successful. Then we store these qubits for A and C1 in quantum memory, and in the next round it's sufficient only to establish this link. So this link has been already established, and we need only to establish the second link. So the idea is actually we split the problem by parts, and in the case of partial success, we do not have to start from the beginning. It's like saving in computer games. So if this part is successful and this part is not, we do not start in the next round. We don't start from scratch, but we already save our result, and then we need to only to establish the lacking quantum link. So then we get advantage, and yes, here let's analyze it, and yes, go to Markov chains. Imagine that P is success probability for one link, and yes, this is a discrete time Markov chain. In each time step, each segment tries to establish a link if this link has not yet been established. P, this 10 to the power minus alpha L, is the success probability for one link. Later we will forget about this exponent. We will write just P. For us, P will be a parameter with the success probability. If all links in here, all 2 links, both links are established, then we perform Bell state measurement. And we can describe our system as a Markov chain, and the possible states of a chain are as follows.
So I have one question. So here, when you say that P is the success probability with where L is the length of the fiber, so there is an assumption. Are you assuming that all these lengths of the fibers are same L, right?
Yes, true. We use this assumption that all links are the same. Maybe it can be justified if this station is in the middle. So if this probability depends only on the distance and the distances are equal, then we can say that this success probabilities are equal. In principle, it's not a critical assumption, so it can be different P can be considered in principle. So it's not a
yeah. So, but I think that is a result which tells you that if it is in the middle, then it will optimize the situation. So taking middle is best, I think. So just wanted to clarify that every links are of same length.
Yes, in principle we can relax this assumption, but here, yes, for simplicity, we assume that all links are the same.
Okay,
and,
thank you.
Yeah, thank you. And here this picture is a copy from our paper. Here, instead of C, A is written here, but it does not matter. These are states of our system. Both memories are empty, so no link is established. Then one link is established, so C1 there is a qubit of in the memory, and of course A. This means that its counterpart, entangled counterpart, is stored in A. Then vice versa. The first memory is empty, but the second memory is full, so the second link has been established, and both links are established. And of course, I must say that technologically, making quantum repeater is challenging, and it's not. It does not exist yet because quantum memory is a problem. We need a technology to transfer the quantum information from a photon to a solid state, and vice versa, on demand to transfer it back from solid state to photon when both links are filled and we want to proceed. And these are transitions. So first, storage map. So let's assume that we start with both empty memories. If we are very lucky and both attempts with both links are successful, this probability is p squared, then both memories are filled. If we are very unlucky, then with probability 1 minus p squared, no one attempt is successful, and we are again with all memories empty. Or intermediate regime, when one attempt is successful and another one is not. The probabilities are p times 1 minus p. And here again the second memory is filled, and we try to fill the first memory. We success with probability p and do not success with probability 1 minus p. And if we are here, then we kept here, but this is a storage map. And the measurement map is actually when both memories are filled, then immediately the well state measurement is performed, and the entanglement between A and B is established, and we assume that that entanglement between A and B immediately used in application in quantum cryptography or somewhere else. So once we have entanglement between A and B, it immediately is used somewhere, and we empty all the memories. So that's why we have such a transition. If we have both memories filled, then we empty both of them, but record +1 point to us. So this is a useful transition. So +1 point, and yes, beginning from scratch for the next entanglement between A and B. And then it can be shown that average waiting time. So how if we start from all memories empty, how long shall we wait for until both memories are filled? And that's approximately equal to 3 over 2p for small p. If p is small, that's approximately like this, against p to the power of -2 without a repeater. So we see the advantage, the gain. And I shall say that one time step includes both maps. Storage map. So first we apply storage map, and then we look. If we have two memories, both memories filled, then we immediately empty them and use this global or Alice-Bob entangled state. So this is our advantage of quantum repeater. The waiting time is of the order 1 over p, not 1 over p squared. If this p establishing one link between A and C1 is still very, very small, we can split these links, these segments further into subsegments. Maybe this p is different from this one. It's already a different model. So here we have already 6 segments, and again, in each time step, each connection tries to establish a link with a success probability p. And once all links in all segments are established, we perform all these yellow stations, perform entanglement swapping, and the long distance entanglement between A and B is established. And then the average waiting time can be derived, is known from the, actually it's reduced to the minimum of independent and identically distributed, geometrically distributed random variables, such kind of expression involving binomial coefficients. It was known in mathematical statistics in this paper by Spankowski and Rego. And in the context of quantum repeaters, it appeared here in 2011 by Bernandes, Prax-Meyer, and Van Log. And further development, memory multiplexing. So let our stations have not one memory, but several ones. So in parallel, in each segment, in parallel, we try to establish not just one link, but several, here 3 links, to increase our chances. Then the state of our Markov chain is already a vector of n times m zeros and ones, characterizing each link with each connection, whether this entanglement is generated here or not.
Sorry, can you kindly go to the previous slide? Just one small thing. So when you are finding out this average waiting time, how this, can you give us this intuition that how this formula for a long chain repeater is coming?
Sorry, intuition, how does it behave in long chains?
Mm-hmm.
It behaves like one average waiting time decays as 1 over logarithm of n. Yes, it can be. It's not obvious how does this expression behaves. It behaves like 1 over logarithm of n. So in principle, waiting time decrease. Of course, it decreases because we have more and more segments to establish to establish a connection, but it decays slowly as 1 over logarithm of n.
Mm-hmm. Okay. Thank you. Oh.
Yes, thank you for the question. Yes. So here we have also a Markov chain when each, for example, these thick lines denote the established links. And inside these yellow stations, we can perform entanglement swapping between arbitrary pairs. For example, we have this this links established, and then we can perform entanglement swapping between these two, between these two, between these two, between these two, and between these two, and establish a global entanglement between this memory in A and this memory in B. So we have like a chain, like such a chain. And in principle, here maybe we are so successful that in one round, at one time step, we can have more than one more than one chain. For example, in blue, we have another chain, of course, using different connections. We cannot use the same connection twice simultaneously in the same time step. So so here in per round, we can get more than one entanglement pair between A and B. If we can construct, if we can build more than one chain between A and B. And in principle, it can happen that we can have two chains and also some established links which do not form a chain, so isolated links. They can be used in later rounds. So in this picture, we have this black chain, and yes, we perform all entanglement swapping and empty all these memories and get +1 point to our task. And then another chain is blue. And also this magenta links, they cannot form chain, but they are useful. And in the next round, we do not start from scratch. We start already with some links established. So it's also an advantage of memory multiplexing that we can use some such isolated links established in the previous rounds for the next rounds. And now we are interested in the average rate of average rate of generation of entanglement between A and B in the stationary or long-term stationary regime or long-term. So what does it mean? So we start. Let me illustrate it here. So we start, for example, from this. Both memories are empty. Then we travel somehow over these 4 states. And on long times, some stationary regime will be established when average time the system spent in each state do not change in time anymore. So some stationary regime. And we are interested in average rate in this stationary regime, average entanglement generation rate in the stationary regime. And now a little bit different scenario, but leading to the same to the same mathematical model. Let's consider not a chain of repeaters, but multipartite repeater or switch. Our reviewers said that it's not good to say repeater about it or router, but it's good to say switch because it is called so in existing papers. So there are multipartite communication tasks, so also like conferencing, for example, confidential conferencing when we now use Teams for a conference, but our conference is not confidential, but it could be confidential, and we could want to have a common conference key. And then the so-called Greenberger-Horn-Zeilinger or GHZ states can be used for this conference key. Or for metrology, for network of quantum sensors to improve their precision. Also, GHZ states are very useful. So so these users A1, A2, and A3 want to have to generate GHZ states. Not just one state, but generated. They want to generate it permanently with the highest rate as high rate as possible. How do they do this? They establish again bipartite links with this central station with the switch. Also, with each link is successful. Establishing each link is successful with some probability p. And then imagine that each user has established a Bell link with the switch, with the central switch. And so we have a tensor product of these Bell states between AI and CI. I is from 1 to n. Then an analog of this decomposition. The decomposition over all Bell states. Here we have a decomposition over all the GHZ basis states. So GHZ, if we apply to a GHZ bit flips on all qubits except the last one, and the phase flip on the last one, and apply or not apply. So this sum over binary vectors of the length n. So we can apply or so we choose either to apply or not to apply the corresponding bit or phase flip. Then we get a orthonormal basis of GHZ states. And we have such a decomposition, and also can be shown using either directly or using stabilizers. But also, if now we see that if the central station C, the switch, performs the GHZ measurement, so measurement of this in this basis formed by these states for various B1, Bn, then the state of A1, An also collapses onto one of these GHZ states. this switch also communicates the outcomes B1, B2, and so on, Bn, and then A1, An. So our users also know which state do they have. And in principle, they can, if they want to have GHZ, not modified GHZ, then they can perform if they know B, they can perform such bit or phase flips, reverse this bit or phase flips to get a GHZ. Okay, let me skip this part with stabilizers. These models are mathematically equivalent, at least in the idealized scenario. In both cases, for a successful event, so GHZ distribution or long distance Bell state, at least one connection in each segment must be successful. So here in the previous model, at least one connection in each segment must be successful, and here at least one connection in each segment must be successful. And here we so what do we have here? This guy has two links with this segment. In this segment, two links are established, and here as well with this guy. I have a different ordering. I know that here with 2, 1, I use not the ordering depicted here 1, 2, 3, but 1 first segment, second segment, third segment. So on the third segment we have all 3 links established, and on the on the second segment, and on the third segment we have 2, the first and the third link established, and we can form like it's depicted here that okay, first this link, and this link can be used to get one GHZ state, and the same here. So this, and this can be used to get a bipartite entanglement between A and B. And also the second successful event is here. So also this link, and this link can be used to establish the GHZ, and this the same here. This link, so this link and this link can be used to establish bipartite entanglement between A and B. And also one more link here and here is isolated, so does not form a chain from A to B, or does here also cannot be combined with some other links to get a GHZ, but this link can be used in the next rounds. Yes, let me briefly explain that first our approximation, small p. So now, as I said, our description of the, where is it here, state of the Markov chain is a vector corresponding to whether each memory is filled or not filled, and if we draw a graph of states, an analog of this graph, it will be very, very complicated because many states and many transitions between them. But let's consider, we can consider the following approximation: small p, or rare events. So success probability of establishing one link is so low that probability of establishing more than one connection is negligible. Consider this problem. And in general, why do we consider approximations? In finding stationary solution of a Markov chain is reduced to a system of linear equation, and so in principle it's not a problem, it's numerically tractable. But we want to have an analytic answer, not numerical, but analytical answer, and we then we need some approximations. And this is our first approximation of rare events. That probability that per one step more than one connection will be established is negligible. So such situation is highly improbable that we have more than one link per round. And then for the case of just bipartite, so return to the very first case, this case, but with multiplexed memories. So by 2 segments, but maybe the number of memories can be larger than 1. Then the states can be characterized as follows: the number of memories in one segment established, and one of the links in the other segment established. So 0, 0, 0, 1, 2, 1, and so on. Okay, maybe I'll skip this because it's not our main result, but just the idea that only transitions between neighboring nodes are possible. So we neglect transitions from 0, 0 to, let's say, 2 times 0. So 2 memories it's a probability that 2 memories simultaneously will be filled is negligible. So we have a relatively simple structure of graph, and we can use Markov chain tree theorem to reduce to find the stationary state. It can be found. So M is the number of memories per segment. So memory multiplexing. Still, it's not very explicit because we don't know. So how the question, how does it behave with M, for example? We don't know. With it's hard to generalize for more than 2 participants, more than 2 segments. The multipartite scenario. However, another approach can be used here also for corresponding to small p, to use a continuous time Markov chain, the Poisson process. So if actually Poisson process is exactly about this, then in each time step, it's we neglect the probability that 2 events can occur on only 1 or 0. Actually, this pirate is the same. It's also small p approximation, but done in a different way, and they get in principle more general results, not just for n equal to 2, but still it's an approximation of small p. And now we go to our main result: develop an approximation based on universal properties of probability distributions, the law of large numbers and the central limit theorem. Let's describe our Markov chain in more detail. Let xi, let k is a time step, and I means the segment. For example, for 4 segments, 1, 2, 3, 4. The number of memories here is also 4, but it's just coincidence. Of course, they do not have to be the same. They can be different. It's just coincidence. And xi is the number of established links for each segment. For example, here, the x1 is 2, because 2 memories here are filled, 2 links are established. X2 is 3, because all 3 links are established. And x3 is again 2, because only 2 links are established here. So the number of established links. So our Markov chain is characterized by the number of established links in each segment. So 2, 3, 2. I. And k is a time step, so time variable. Then storage map. We try to establish new links. So for example, here on the first segment, we succeeded to fill 1 more link. Here we succeeded to fill 2 links. Here 1 link, and here we in the 4th segment we didn't succeed to establish a link, and we so this. Then the probability of y is the number of new established links. It's distributed according to the binomial distribution, because each of the remaining m minus x links, if x links are already filled, then we try to fill each of m minus x links, and the success probability is p. This is a binomial distribution. So y links are successful with such a probability p to the power of y. Other links m minus y are unsuccessful, and this is a binomial coefficient. Then LK is the number of links the minimal number of links between A and B. So look, if in this situation, in each segment we have at least 2 links. This means that we can generate 2 GHZ states or 2 Bell pairs between long distance Bell pairs, depending on our scenario. So we are exactly in this like on the figures we saw above. So before this, here we don't we cannot establish a global entanglement between, because the second segment has no links at all. So second segment is missed. But now we already at least 2 links in each segment. This means that we can generate 2 successful events, so successful GHZ states or successful long distance Bell pairs. And we subtract, we empty these memories, we subtract this number 2, subtract 2 from this all columns, and we start the next round with such state 1, 0, 0, 1. So we empty all memories in second and third segments, and but 1 link in the first segment and 1 link in the last segment are still here, and we can use them in the next rounds. This Markov chain is complicated because what is the difficulty? This minimal operation, so LK, the number of successful events, is minimal over all segments. This makes all these processes dependent on each other. Let's consider a simplified model. A simplified model. Yes, this is an explanation why this model is analytically intractable. The random processes xi, k for different I are dependent because of these red operations. Operations are written in red. Lk depends not on one xi, but on all xi's, and then this number is subtracted from each xi. So and much more simply is replace Lk by a fixed number L. Previously L denoted distance, forget about it, now L is completely different, by a fixed number L. Then all processes are independent now because L is fixed, and now xi in the next time step depends only on xi and yi on the previous time step and the fixed number. So all these processes are now independent. It's easy to analyze this model, but how to justify this replacement? The justifications comes from the law of large numbers. Actually, I noticed it from simulations and intuition from the law of large numbers. On the long-term scale, if we are interested in a long time and many repetitions, then the fluctuations of this LK around the expectation value do not matter. So let's replace LK by, let's say, its average value, which is fixed. This is a justification. But the law of large number is a universal property. It doesn't assume that some parameter like p is small or large. It's a universal property of the probability distributions. Then again, we have such a simplified model. Sorry, this is a typo. Of course, we subtract not this minimum anymore. Yes, this formula is correct. We subtract L, the fixed number L here. Fixed number L, not LK, but L. And of course, previously, our model was such that xik cannot be negative by construction because we subtract minimal value of xi plus yi. But now if we subtract, instead of LK, we subtract a fixed number, that there is no guarantees that it is smaller than xyk minus 1 and our plus y ik. No, so x can be negative, which is unphysical, so the number of field memories cannot be negative. But new requirement, L must be chosen to be the maximal value such that expectation of minimal xi for long times is non-negative. Again, why do we allow negative x? Again, law of large numbers, fluctuation to negative region do not matter if on average the long-term minimum over ik is non-negative. So expectation of the minimal value must be non-negative. But if some fluctuations touch the negative region, it does not matter. This is I use the following financial analogy. So let's assume the first model, xi, k is the wealth of ith person in a village in the beginning of the year k, and y is the profit of this person in the year k. In the end of the year, a governor comes and looks to the wealth of the poorest man, so xi plus the profit, and takes the corresponding amount from each person. So the poorest guy remains with 0 wealth after that, and other remain with some non-negative wealth. So this governor looks for the poorest guy and takes the corresponding amount of money. And another scheme. Now this governor takes a fixed number of money, and if you don't have such money, you can borrow. It's not a problem. People can borrow money. So if xi is negative, this means that then can borrow. But the government wants to maximize the tax, but such that on average the minimal wealth among the parties must remain non-negative. So of course government doesn't want that that the participants, people go to the negative region for a long time. So they can borrow for some time, but on average on long time they are non-negative. And intuition from the law of large number justifies this assumption. This intuition. And one more assumption. Let's assume that this xi are distributed according to the normal distribution. We can actually noticed this from simulations, and of course it's justified by intuition of the central limit theorem. Then this model is easy to analyze, and we can derive a nice closed form expression for the rate of long-range entanglement between A and B, or GHZ, a generation rate in the multipartite scenario. Alpha depends on N, beta depends on P, gamma is Euler-Mascheroni constant, known the famous constant in mathematics. And this plot is a comparison between this formula dashed and simulations, exact simulations. And we show excellent agreement even for small n. In principle, we use asymptotic results like limit theorems, and and in the next slide I will show this. But like in probability theory, and let's say in semi-classical on WKB approximation, Wenzel-Kramer's Brillouin approximation in quantum mechanics, formally it must work only for large n, but in practice it gives good results also for small n. That's the magic of this method. That's fantastic. So in principle, it should not work for small n, but it works also quite precisely, quite accurately. Well, very briefly, the states of the derivation. The first, our model is quite simple, and we can, using some derivation, we can derive recurrent relations between expectations of xi and variances. So these are recurrent relations between them. From then we can derive stationary values for k goes to infinity. Now we use the assumption that they are normally distributed. If they are normally distributed, and we know expectation and variance, then we know distribution. And now we use the result from the probability theory, expectation value of the minimum of the normally distributed random variables. So again, as I said, formally, this formula is true in the limit of large n, but as we saw, it works fine also for small n. And then finally, we find the maximal L such that this right-hand side is non-negative. So again, some fluctuations to negative values of x are possible, but on average, a long-term minimal value of x must be non-negative. And we get this value of L as a rate. So this is the main result, and further questions. Of course, if we are mathematicians, that we are interested in rigorous proof, because as I said, sorry.
Sorry. So in the last slide, I was about to ask this question about this decoherence. So in the last slide, you mentioned about this decoherence. So in most of the cases, what happens? The states are stored in memory and undergo decoherence, and that's why we basically model them as a depolarizing noise. So when you are assuming the probability, you are just you are considering the link generation probability, right? So is there a way how you are if you incorporate this decoherence noise, things will change both in bipartite and multipartite scenario?
Yes, that's a good question. Of course, yes. Further question is consideration of more realistic scenarios, because we have idealized scenario, only success probability is less than 1. That is the only source of imperfection. But in practice, we have decoherence, we have noise. There is a lot of open questions here. I think it can be. I think it can be taken into account, because if decoherence or noise is Markovian, then the Markovian property is not violated, and we can adapt our Markov chain for this case as well. So our approximation is quite universal, is not relied on this how to say, idealized scenario. So I think it can be done, but of course it has not yet been done. So it's a future work.
So
I'm interested in it.
Thank you. Another question corresponding to this is that, yeah, in this noise model, so there is something which gives e to the power to minus t by capital T, while minus t is the memory the time that it is staying in the qubit is staying, and the capital T is the intercoherence time of the network. Now, if the capital T is low, if the capital T is low, many of these it will not go up to this. So it can restrict. What I'm thinking is that this success probability gets restricted with this capital with the intercoherence time of the network.
If I understood you correctly, so you said that there is a capital T time of decoherence. So after that, people, for example, from these papers typically consider that if, as I said, let's say this link, which was not used for some time, then it is emptied. So because we don't trust this entanglement anymore, because it has been decohered, and drop it. Then it will lead to more complicated Markov chain. For example, here we can rotate here for infinite time. For example, this memory is filled and this memory is not filled, and we are unsuccessful of filling it. Then we again successful, but we cannot get from here to here back to here. But in your scenario, if we consider decoherence, so or a finite lifetime of each memory, then we will get also this type of transitions, or more complex, or we will have more complex equations here, not just x plus y minus L, but also minus decoherence will be somewhere here. So yes, it will be a more complicated model. I hope that still, at least in some scenarios, it can our analysis can be generalized. But I'm interested in to do this because yes, I understand that it's for practice. It's interesting, of course, for practical case, not for the idealized case.
Right. Thank you.
Yes, and actually, yes, and what about rigorous proof? Because I used some intuition, but not a rigorous proof. I thought that maybe it's not necessarily, because it's not a probability theory, it's like theoretical physics, so we derived formula which works, and that's all. But then I was not aware that this topic is more popular than I thought, that our paper is under review, and reviewer gave us some papers we were not aware of, so I didn't realize how important is this topic. For example, I was not aware of this paper by Vardoyan, Guhan, Nain, and Tausli, and some others, and or Hatri. And since this topic is popular, then maybe it makes sense to prove rigorously. I'm not sure. So these are further questions. And actually, that's what I wanted to tell. So main result is analytically tractable approximation based on universal properties of probability distributions, namely on the law of large numbers and the central limit theorem. And this approximation gives excellent agreement with simulations for the whole range of parameter values. Thank you for listening.